Continuing with where we left off on Wednesday, we will do a few additional example problems. So we have an example problem here where we have a reverse osmosis unit and we are to demineralize brackish water at a flow rate of 760 cubic meters per day. We're given the water permeation constant of 0.2068 liters per day per meter squared per kilopascal at 25 degrees C. The transmembrane pressure is 2400 kilopascals. The difference in the osmotic pressure between the feed and the product waters is 310 kilopascals. We're also told that the lowest operating temperature is 10 degrees C. And we're told that the area needed at 10 degrees C is 1.58 times that needed at 25 degrees C. We're asked to determine the membrane area required and the number of element modules required, assuming that each element has 30 meters squared of membrane surface area. Let's just write down the information that we have. So we have Q equals 760 meters cubed per day. Permeation constant is 0.2068 liters per day per meter squared per kilopascal at 25 degrees C. Transmembrane pressure is 2400 kilopascals. Difference in the osmotic pressure is 310 kilopascals. The lowest operating temperature is 10 degrees C, and we are told that the area at 10 degrees C is equal to 1.58 times the area needed at 25 degrees C. Remembering the equation for the flux of water is equal to Kw times delta P minus delta pi, and that is equal to 0.2068 liters per day per meter squared per kilopascal times 2400 minus 310 kilopascals, and that is equal to 432 liters per day per meter squared. There's a question on Wednesday about flux. Remember, the flux of water is equal to your flow rate divided by the surface area of the membrane. So we can calculate the surface area of the membrane, and that is equal to 760 meters cubed per day times 1,000 liters per meter cubed divided by the flux, which is 432 liters per day per meter squared. So meters cubed cancel, liters cancel, days cancel, and we're left with meters squared, and this is equal to 2,780 meters squared. Now we said that the membrane area is equal to 30 meters squared, so that's per element. And typically the area ranges from about 3 to 60 meters squared per element. So in order to determine the number of elements we need, 2,780 meters squared divided by 30 meters squared per element, and that is equal to 93 elements. Similar to when we talked about filtration, how in filtration we needed an even number of elements, we need to think about the same with membrane systems. with membrane systems, plumbing these systems is extremely expensive. So we said we needed 93 elements. Now, typically, your membrane systems consist of a vessel, and inside the vessel are the membrane elements. And I've shown this with 5 elements. Let's assume we have 6 elements per vessel, and that's about the maximum that you'll find in a vessel. So now, we've got 6 elements per vessel. If we have 16 vessels, think about this here. Each one of these circles is a vessel. So we have, each one of these is a vessel, and we have 6 elements per vessel, and we have a total of 16 elements, 16 vessels, times 6 elements per vessel, and we have 96 elements. So instead of the, we calculated 93 because of plumbing requirements and wanting simplicity of plumbing. We will instead design our system so that we have 16 vessels, 6 elements per vessel, and that means 96 elements, which means we can actually produce, or we can actually treat a little more than 760 meters cubed per day. So far, all of the equations that we have been using pertain to reverse osmosis systems. However, with ultrafiltration and microfiltration systems, the equations are slightly different. And again, the rejection is essentially the same. So we're looking at the difference in the concentration in the permeate and the concentration in the feed. Very similar, essentially the same. The flux here is, again, notation changes a little bit. Instead of F sub x, we use J. Again, that is the flow rate divided by the surface area of the membrane. Now, with microfiltration and ultrafiltration, the flux is then equal to the transmembrane pressure divided by the dynamic viscosity of the water, so it's dependent on temperature, and the resistance coefficient. Now, R sub m is for a clean membrane. Notice here we add 2 additional terms, a resistance coefficient for irreversible, really irreversible fouling, and for reversible fouling. And I talk a lot more about fouling in the main recorded lecture, so you can watch that for more information. So let's look at this example problem. We are told that Yeehaws winter demand is 10,400 cubic meters per day, and its summer demand is significantly greater at 15,600 meters per day. You're asked if the membrane filtration system is designed for the winter demand, can it meet the summer demand with the same area of membrane? You're provided a number of parameters. The maximum transmembrane pressure for this system is 152 kilopascals, but you were to operate the system at 75% of the maximum transmembrane pressure. You were given a resistance coefficient of the clean membrane at 2.94 times 10 to the 12 inverse meters, and you're told that the winter temperature is 4 degrees and the summer temperature is 20 degrees. So we need the dynamic viscosity. We can look that up in the appendix in the textbook. And at 4 degrees, this is 1.567 times 10 to the minus 3 Pascal seconds. And at 20 degrees, it is 1.002 times 10 to the minus 3 Pascal seconds. So, using the equation, our flux is equal to Q over A equals delta P, the transmembrane pressure, divided by the dynamic viscosity times the resistance coefficient. This is equal to 1,400 meters cubed per day. Divide that by the area. We have the viscosity in Pascal seconds, so let's convert this. We have 86,400 seconds per day. Days cancel. That is equal to 152 kilopascals, but we're going to operate at 75% of that. There are 1,000 pascals per kilopascal. Divide that by the viscosity at 4 degrees. Remember, we've designed it for the winter demand. So 1.56 times 10 to the minus 3 Pascal seconds times 2.94 times 10 to the 12 inverse meters. And if we solve for area, that is equal to 4,864 meters squared. So that, remember, that was designed for the winter demand. We can't change the area once we've designed it. So now let's look at 20 degrees C. What would the flow rate be? And that is equal to delta P times the area divided by the viscosity times the resistance coefficient, and that is equal to 152 kilopascals times 0.75 times the area that we just calculated, divided by the viscosity at 20 degrees, times the resistance coefficient, and that is equal to 0.188 meters cubed per second, or 16,264 meters cubed per day. We needed 15,600, so yes, we can meet the summer demand with this membrane area. So the membranes that we've been looking at so far are spiral wound membranes, and I provide significantly more information about these spiral wound membranes in the roughly 50-minute lecture that provides the theory of membrane filtration systems. Another type of membrane are hollow fiber membranes, which you see here. And these are tubular membranes. They range from these kind of almost looking like spaghetti like membranes to these ceramic, very rigid tubular membranes. And you can see here this is actually in a membrane bioreactor used for wastewater treatment. And these are inserted into an activated sludge tank. The treated water actually flows through the membrane, and the way these work as a outward or an outside in membrane. So the water flows in from the outside through the tubular membrane and out through the center. Now these ceramic membranes actually operate as inside-out membranes where the water flows into these tubular membranes and then out through the walls. So again, here we have an outside in membrane, and here we have a inside out. It's really in terms of the flow direction in these membranes. So let's look at an example problem here where we have an ultrafiltration membrane. It contains 5,760 fibers. So think of those long kind of spaghetti-like fibers that you saw in the previous image. The fibers are 1.87 meters long with an outside diameter of 1.3 millimeters and an inside diameter of 0.7 millimeters. And you're told that the volumetric flux is 75 liters per meter squared per hour. You're asked to calculate the water production from one module if the direction of flow is outside in or then later inside out. So the area per fiber is pi times the diameter times the length. So that's equal to pi times 1.3 millimeters, 10 to the minus 3 meters per millimeter, times 1.87 meters, that's the length, and that is equal to 7.64 times 10 to the minus 3 meters squared per fiber. So the flow rate is equal to the flux times the area, and our flux is 75 liters per meter squared per hour times 7.64 times 10 to the minus 3 meters squared per fiber times 5,760 fibers. And that is equal to 3,300 liters per hour. Okay, so this is with an outside in configuration. Now, with an inside out configuration, it's the area that will be different. So the area equals pi dl. Now we'll use the inside diameter, and that is equal to pi times 0.7 millimeters times 10 to the minus 3 meters per millimeter times 1.87 meters, and that is equal to 4.11 times 10 to the minus 3 meters squared per fiber. Again, we can calculate Q simply equals to our flux times the area. And again, we have 75 liters per meter squared per hour times, in this case, it's the 4.11 times 10 to the minus 3 meters squared per fiber times 5,760 fibers, and that is equal to 1,780 liters per hour. Okay. So it's going to write it up on the top since I'm running out of space here. But if we're looking at the difference between the outside in versus the inside out, that is equal to 3,300 liters per hour divided by the 1,780 liters per hour. And if we multiply by 100%, and that is equal to 186%. So what that's showing is that the outside-in membrane produces 86% more than the inside-out configuration. So it just gives you a sense of the difference in terms of configuration, whether we use an inside-out membrane or a outside-in. And as I've showed previously, with the membrane bioreactor, you can see those operate as an outside-in. Most of the work that I've done with ceramic membranes are actually operate in an inside-out membrane. So the flow is into the membrane, into the tubulars of the membrane, and then out through the outer walls. So hopefully this helps you have some better sense of how we design and operate membranes, and will also help with the homework.